Okay, so we're going to start off by looking at section 7.5, which is on sum and difference identities. Now, 7.4 was on identities as well. What we're going to do with identities this time isn't as abstract as 7.4. Like 7.4 had no calculations at all. We're going to have some calculations in this section where we have to find like an answer, a number. All right, so it's not quite as, it's a little more concrete. And the first thing to look at is this. These two things are not the same. When we have something like this in parentheses, a lot of times we don't want to have plus something or minus something. We just want to have an x. So the idea is, how could you make it just an x? Could you take sine and just like distribute it? No, you can't. You can't do that at all. That's completely wrong. So there is a way to deal with having this plus 3 and get rid of it. And that's what we're going to look at. There's actually six different formulas we're going to look at in this section. You could have sine with a plus inside, or you could have sine with a minus. Then you could have cosine with a plus, cosine with a minus, and tangent with a plus, and tangent with a minus. We don't focus as much on tangent. We really focus more on sine and cosine. But when you have a plus or a minus inside the parentheses, that's called sum or a difference. So how do you deal with a sum or a difference inside parentheses? And that's what I'm going to show you. Okay. Everybody understands, though, that these two things are definitely not equal. That does not work at all. Okay, so what does work? Well, I think I'm going to start off with not showing you sine of a sum. I'm going to do cosine. I'm going to start off with that one. And the formula I'm going to show you is if you have a difference, and it's specifically for cosine. We also don't go through the proof of this formula. Okay, when I do an example, I can kind of prove to you that it works, but we don't prove this formula from scratch. This is called the cosine difference formula. Usually these two things, if you're doing a problem where you're going to calculate a value, those would be numbers, alpha and beta. And usually, I mean, technically they could be any numbers you want, but most of the time, they're multiples of 30 or 45. And every problem we do, these two numbers will be multiples of 30 and 45. So like 60 and 45, or something like that. And when I read this, you're usually going to hear me refer to the one that I circled in red as the first. I call that the first angle. And the one that I circled in black, you'll hear me say the second. So the way I read this is cosine of the first, cosine of the second, plus sine of the first, sine of the second. And if you're kind of wondering, well, why would you even take something like that and write it like that? I'm gonna show you in a second. Okay, so proof is on page 409. It's a little bit more complicated than what we would go through, so we're not going to do that. Everybody have that formula written down. All right, so how do you use it? Well, there's a couple ways you can use it. One is to do an actual proof. Another way, which is a little easier, is to just find an answer. And what I want to find here is the exact value of the cosine of 15. Now, to do this, we have to remember some exact values we've done before. Cosine of 45. Okay. That number, 0.707, comes up a lot. If you do sine 45, it comes up again. If you do sine negative 45, it comes up again. So 0.707 is kind of an important number we need to remember. Does anybody remember 0.707 involves a square root? When we talked about special right triangles, we had two square roots that came up a lot. Does anybody remember what 0.707 has something to do with?
Square root 2 over 2.
Yes, 0.707 is the square root of 2 over 2. And we proved that back when we did unit circle and we did like the 30, 60, 90 and the 45, 45, 90. That was one number we worked with a lot. So just kind of not really part of this problem, but something you need to remember is that 0.707, that's the square root of 2 over 2. And there's one other number that comes up quite a bit. That would be, no, I did that wrong, sine 60, 0.866. 0.866 has to also do with a square root. Does anybody remember the other square root that we studied when we did special right triangles? Square root of 2 came up in a lot of problems, and square root of 3. Square root of 2 and square root of 3 came up a lot. 0.866 is the square root of 3 over 2. If you can remember those two decimals and what they come out to, that's all you need to know to do any problem that's set up like this. So we'll just keep those off to the side and remember those two facts. Okay, so they want to know the cosine of 15. So why don't we just do that and type in, okay, it's 0.9659. So why can't I just write that down and be done? Yeah? That number's not exact. The answer, problem didn't say find the cosine of 15 and round it. If it did, well, then we just write that down to however many decimal places they wanted. They said find the exact answer. When you're finding an exact answer in a problem like this, it's going to have a root in it. So this is how we do it. You have to write the cosine of 15 as a difference of two angles. You might say, well, there's a lot of ways to write cosine, to write 60 as a difference. You could say 70 minus 10. But there's a trick. You have to write 15 as a difference between two numbers, but the numbers have to be multiples of 30 and 45. So can anybody think of how we could write 15 as a subtraction problem? And the numbers have to be multiples of 30 and 45, yeah?
You do 5 and 3.
Do what?
5 and 3.
How would you subtract those to get 15?
Oh, sorry.
Yep.
45 minus 30.
45 minus 3. Yeah, that works. If you're thinking of other ways, there might be other ways to do it. But 45 minus 30 does give you 15. Does everybody agree with that? Okay. Now, we have two angles. Those two angles that we just wrote down are like alpha and beta in that formula. That's alpha. That's beta. So now, take this formula, and instead of writing alpha and beta, I want you to fill in what we just figured out for alpha and beta. Alpha is going to be a 45, and beta is going to be a 30. And when we do this out, it's going to give me the exact answer for cosine of 15, which I can double check because I know the approximate answer. So let's write it down. So it says to do the cosine of the first angle. What's my first angle? 45. And these are all going to come out to nice numbers that we should recognize. So cosine of the first, times cosine of, what's my second angle? Yeah, 30. The second angle is whatever comes after the minus sign. 30 plus sine sine of first angle. First angle again is 45. And then the sine of my second angle, 30. So any questions on how we took this? I would have put it right underneath, but I didn't have enough space and changed it to that. Okay, so now we've got 4 expressions to evaluate. Let's start with cosine 45. Cosine 45. You do not want to write down that decimal. We want to write down what we know that's equal to. What is 0.707? If you write that as an exact answer.
Square root 2 over 2.
Yep, so this is square root 2 over 2 times cosine of 30. 0.866. Again, don't write 0.866. Tell me what that is exactly. Yeah?
Square root of 3 over 2.
Square root of 3 over 2. Plus, now we've got sine 45. Well, that's 0.707 again. Times the sine of 30. That's going to be the nicest one. That's just 0.5, but we could write it as 1/2. So now let's combine that all together. And let's see if when we do that, it actually gives us the answer that we know is right. We already know that's the cosine of 15. Well, let's see if this somehow gives us the cosine of 15. Okay, when you multiply these two together first, and then multiply those two together second, you just go straight across. The square root of 2 times the square root of 3. You can write that as the square root of 6. And then in the bottom, 2 times 2 is going to give me 4. Good. Calculus is paying off here. We got 2 times 2. All right, next one. Square root of 2 times 1 gives me square root of 2. And 2 times 2 again is 4. And now we can add those fractions together. When you add them together, what do you need to make sure you have anytime you want to add fractions? Yeah? Yeah, you got to have the same denominator, but we already do. So literally, we just put them together. There's nothing you can do to combine square roots. So you just say square root of 6 plus square root of 2. And the denominator, when you're added, you do not add the denominators. You keep the common denominator. And that should be the exact answer for cosine of 15. By splitting 15 up into a difference of 2 fractions. Is that the only way to get the exact answer? No. There's other ways. But that's one way to do it. If you know the formula to split 15 up as a subtraction problem. So let's check and see if that comes out the same as what we just typed in. Alright, so you got square root of 6. Yeah, it's just to check the answer. You don't have to type this in. Plus square root of 2. And then divide by 4. 0.9659. And that's exactly what you're supposed to get. Okay, so my graphing calculators, they can't give you this answer when you type in this problem. They're going to always give you a decimal. But the decimal's still handy because you can double check if the answer you got is correct. Yep.
Where'd you get the 1/2 in the formula? I got caught.
That was from the sine of 30. So this is the cosine of 45. The next one is the cosine of 30, the plus sign. The sine of 45 is root 2 over 2 times the sine of 30 was 1/2.
Oh yeah, that makes sense. Because I thought it'd be the same because it's at Sign on. Right.
Yeah, so this one is that one. And then this one is that one. And this one is that one. And this one is that one.
Yeah.
All four values. Yeah.
Would you have to simplify the answer by combining terms or anything, or would you just?
There's nothing you can do with that. You cannot add square roots together. If you had something like this, like square root of 3 plus square root of 3, those can be added together, and you can say 2 square roots of 3. But when you have different square roots, like square root of 6 plus square root of 2, there's nothing you can do. And a lot of times when you're finding trig functions of angles that are multiples of 15, you're going to see something like square root of 6 plus square root of 2 over 4. You might see square root of 6 minus square root of 2 over 4. You might see the order switched with subtraction. That makes a difference. But it always has a square root of 6, a square root of 2, and like a 4 in there. Pretty much every one of these problems. Any question on that one? So when we did unit circle, we were able to find the 6 trig functions of multiples of, let's see, 30, 45, and 60. Those 3 angles were kind of in the middle of the quadrant. The 2 that we were missing were the 15s. We never learned how to do 15 or how to do 75. Now, I haven't shown you 75 yet, but I just showed you 15. So now we can find not just the 30s, 60s, and 90s, but now we can do all the 15s. And technically, if you can do the 15s, you can do half of 15. You can do the 7.5s. And then if you can do that, you can do half of the 7.5s. Then it starts to get a little messy. But 15s is what we're going to focus on.
So when you have cosine of 15 or like any other trig function of 15, is it always going to be reduced to 45 minus 30 degrees?
Well, it's always going to be reduced to something minus something, and those 2 numbers have to be multiples of 45 and 30. Like if I wanted to do, let's say, this angle right here, 15 degrees after 90. That'd be cosine 105. I've got to figure out a way to write 105 as a subtraction problem. Sometimes that's the hardest thing. Something minus something has to give me 105. I would do 135 minus 30. So for 105, that's how it would split up. This is 45 times 3, so that's a multiple of 45. And that 30 is a multiple of 30. So you got to figure out how to write that as a difference of the 2 numbers. Yeah, it might not always be 45 and 30. All right, let's try this one. This one says to verify that this equals that. So a little bit different than calculation. Okay, we're not going to get a number for an answer this time. We're just going to try to simplify the left-hand side. Now, look at the left-hand side. It's a cosine, and there's a difference. We have a formula for the cosine of a difference right here. Cosine first, cosine second, plus sine first, sine second. And the plus is the opposite of what you had right there, the minus. So let's apply that to this. That's my first. That's my second. So I'm not going to do anything with the right-hand side. I'm just going to try to work with the left-hand side until I simplify it into the right-hand side. And simplifying it when you have subtraction in here, it's not as easy as you would wish, you hope it would be. You've got to do that formula I showed you. That is the only way to simplify a difference inside. So it's cosine, cosine. Put the opposite of what you had right there. Sine, sine. Okay. First angle, second angle, first angle, second angle. That's the pattern. What's my first angle? Pi over 2. What's my second angle? Theta. Not going to be able to do much with the theta because that's a variable. But pi over 2, we're going to figure that one out in a second. Okay. What's my first angle? Pi over 2. And my second angle? Theta. So the cosine theta and the sine theta can't really do anything with them. But let's find the cosine of pi over 2 and write that down. Just like we did here. We're going to find each one of those. Well, the ones that are numbers. Since I'm in degrees, I'm going to do it that way. What's pi over 2 in degrees? Yep, 90. That's 90. If you don't want to do degrees, that's fine. Just change your mode to radians. But I'm in degrees, so let's just type in 90. And we get 0. So 0 times the cosine plus, let's figure out the sine. Sine of 90, or pi over 2 if you want to do it in radians, is 1. So that simplifies to that. Now, what's going to happen in this step?
When you multiply 0 times cosine theta, you're just going to get 0. So it's going to be 0 plus sine theta plus 1. So you're, times 1. So you're just going to have sine theta.
So yeah, this 0 times anything, 0 wipes that out. And 1 times sine is just sine. So 0 plus sine, which we don't even need the 0 really. 0 plus sine is just sine. And that's exactly what they wanted me to prove. They wanted me to show that if you apply the formula I just taught you to the left, it turns into the right. And it does. So there's still some proofs in this section, but they're not as hard as the proofs in the last section because you're using a predetermined formula every time that has a very specific pattern to it. And it makes it very easy to show that something like this equals something like that. Any questions before we'll try one more of those? Yeah?
I think I missed that. How did you just get rid of the cosine thing?
Well, the cosine of 90 degrees is 0.
Okay.
And 0 times anything is 0.
It's 0. Okay. But then where did the 1 go? With the, I guess it's just itself.
Well, 1 times sine, it's just itself.
Yeah.
So 1 times sine is just sine. Let's try that. Let's try this one. So this is cosine of pi over 2 minus, cosine of pi minus theta. So let's start with just kind of like the template of that formula. To rewrite that using my formula I just showed you, you don't have to fill the angles in yet, but can somebody tell me what comes first? Yeah? So the whole formula.
Oh.
Just the trig functions.
Cosine of alpha.
Okay, don't even worry about that yet. So cosine of the first. And what comes next? The second. Right, we'll fill that in after. And what symbol do we put right here? Opposite of what you had there. And then what comes next?
Sine of the first.
Sine of the first. Sine of the second. Now fill it in. First, second, first, second. Pi. Theta. Pi. Theta. Now, you're not going to be able to do anything with the thetas. Those are variables. But we can plug in the pi's and see what those come up to. Again, I'm in degrees. I just don't want to change to radians. What's pi? in degrees? Yep,
180.
180. So let's just plug in cosine 180. I get negative 1. So negative 1 times cosine theta plus, now we're going to fill in sine of pi, which again is 180. Sine of 180 is 0. So that's 0 times the sine. Okay. What's going to happen at this step? Yep.
Sine pairs going to cancel out.
Right.
Multiplying by 0.
Multiplying by 0, so that's gone.
And then you're multiplying cosine theta by negative 1, so the answer is just going to be negative cosine of theta.
Yeah, negative 1 times cosine is just negative cosine theta. And that's exactly what they told me that I should get. So we took the left-hand side and we simplified it until we got the right-hand side. And that's it. Any questions on that one? So out of the two problems, this is the harder type, I think, because it's like an identity. This is more numerical, so if you don't like working with identities, you're really actually finding a number that's an answer to the problem. Okay. But you'll see both of those kinds of things on the test. All right, so now when we want to look at the cosine sum formula, there's really only one thing there that's going to change. Does anybody have a guess on the right-hand side? What would change to make this the sum instead of the difference? Yeah?
Addition sign.
Yeah. The only thing that's going to be different is that. So let's write it down. Did I write it down? Okay, I'll just forget. So this is the cosine sum formula. Still cosine, cosine. Still sine, sine. Still first, second for the angles. But the symbol that you put between the cosines and sines is the opposite of the one that you had right there. Well, at least it's the opposite when we're dealing with cosine. When we deal with sine, it's a little different. But there's your cosine sum formula. So now what that enables us to do is it just gives us a little bit more flexibility, gives you some more options. So instead of writing something as a difference inside the parentheses, if you think you can do it as a sum, well, we can work with that too. So now we can do things as a sum or a difference. So let's look at 75. Can anybody see a way to write 75? And it's okay if you want to do a sum of two numbers. But they have to be multiples of 30 and 45. Yeah?
30 plus 45.
Yeah, we just do 30 plus 45. And that's how we're going to do it. But technically, anything you can do as a sum, you can do as a difference. Does anybody see how you could write 75 using subtraction? Yeah?
105 minus 30.
105 is not a multiple of 30 or 45. So the two numbers we start with have to be multiples of 30 and 45. Otherwise, that would have worked. Yep? 15 is not a multiple of 30 or 45. else see how you can get 75 as a difference? Yep.
135 minus 60.
135 minus 60. I mean, how do you figure that out? I don't know. You just have to use one number that's a multiple of 45. The other number has to be a multiple of 30. You're always going to need one of each. And you just have to figure out how to add or subtract them to get 45. So if you wanted to do this problem, you could use the first formula I taught you and do it as a difference. Or you could use the second formula I taught you and do it as a sum. When I ask people, it seems like people got this answer really quick. People kind of struggled to figure this out. So maybe in this case, it would be easier for you to think of it as a sum. But either way. Okay, so let's use the sum formula. Cosine, cosine. Sine, sine. And what's going to go between them? A plus or a minus? Yep. Minus. It's, for cosine, it's always the opposite of whatever you put right there. Okay. And what am I going to fill in for my first angle? Yep. 30. 30. And my second angle? 45. 45. And 45. And here is where we need to remember those 0.707 and 0.866 numbers. Let's check them. Cosine of 30, 0.866. Yep.
That's the square root of 3 over 2.
Yep. That's the square root of 3 over 2. Cosine of 45, that's 0.707. What's the cosine of 45?
Square root of 2 over 2.
Square root of 2 over 2. There's how your square root 6 is going to pop up in this problem. Minus. Sine of 30, we're just going to put 1/2. And does anybody remember the sine of 45? We did that a couple of problems ago. Yeah.
Square root 2 over 2.
Yep. Okay. So let's multiply it together and see what we get. What do you get when you multiply together what's in that box?
Root 6 over 4.
Root 6 over 4. And Sam, what do you get when you multiply together what's in that box?
Square root 2 over 4.
Square root 2 over 4. And now we can combine it together. Just make sure you have a common denominator, but in these kind of problems, you always will. So we're just going to put it all together. Yep.
Square root 6 minus square root 2 over 4.
Very easy to check your answer. Type that in on a calculator, see what you get. Type in cosine 75, see what you get, and they should come out as the same decimal. Any questions on that one? Yeah.
No, I just realized we pretty much got the exact same answer for finding the exact value of cosine of 15 degrees, except we just changed the sign. Is that because they're like, was it complementary that add up to 90?
Yeah.
Is it because they're complementary, or?
Yeah, it might be. I'd have to check that maybe with a couple other angles, like we did the 15 and the 75. We could check the 105 and the 165 and see if the same thing happens. And if it does, then we could try to prove that. But I have a feeling that might be right. All these answers are going to end up with variations of root 6, root 2s, and 4s. Sometimes they're plus, sometimes they're minus. Sometimes you have another minus in front like that, so you have 2 minuses. Sometimes the order here is switched. But it's always a variation on that. Yeah, very good. Okay, so we've done the cosine sum and difference. Now let's look at the sine sum difference. It's kind of similar, but it's a little different too. Does anybody see what's different about the structure of how this is set up? Yeah?
Instead of there being two cosines and then adding two sines, it's a sine times cosine plus cosine times sine.
Right. This is what I call mixed. The sines and cosines are mixed together. Versus when we had a problem like this, the sines and cosines were grouped. The cosines were grouped on one part, the sines were grouped on the last part. Now they're mixed. And the other thing to notice is look at the sign between them. It's a plus. It was a plus. So when we're dealing with the sine formulas, whatever you put here is the same thing you put there. With cosine, it was the opposite. So that's the sine sum formula. Anybody think they know what the sine difference formula is going to be? Or you could just tell me what's going to change from that formula to get the difference. Yeah?
Sign will change.
Sign
isn't S-I-G-N.
Yeah, the addition or subtraction symbol between the two sets of parentheses, that's what's going to change. So it's going to become a minus sign instead of a plus sign. So now what this enables us to do is find like the sine of 15, the sine of 75, things like that. We can go through one if you want. I won't do 15 or 75. I'll pick a different one. But it's going to end up as some variation of root 6, root 2, and a divided by 4 in the denominator. It's always going to end up with something like that. All right, let's try sine of... I got to pick a multiple of 15 to make this work. So let's do, what's 15 degrees past 180? 195. So now you have a choice. If you can figure out how to write 195 as a sum, great. If you can do it as a difference, that works too. So you pick how you want to do it. Either a sum or a difference. But the two things you add together have to be multiples of 30 and 45. Otherwise, you're not going to get decimals that you recognize. Yep.
135 plus 60.
Yep. That's what I was kind of thinking of. 135 plus 60. And now let's write it all down. Sine, cosine. Cosine, sine. The reason I switched the order of the sine and the cosine is so I could keep it first, second, first, second. I just like the angles to always be 1, 2, 1, 2. There's other ways. I mean, you can write it differently. All right, sine, cosine, cosine, sine. Sine, cosine, cosine, sine. 1, 2, 1, 2 for the angles. 1, 2, 1, 2. And when we're doing a sum, what symbol goes between them? Yep.
Plus.
Plus. You keep it the same. Now we just have to do all 4 of those out and see what we get. So sine 135. 0.707. What is 0.707? Well,
the square root 2 over 2.
square root of 2 over 2. Okay, cosine of 60. 1/2. Cosine 135. Okay, what's that one? Yeah?
Negative square root of 2 over 2.
Negative square root of 2 over 2. And sine of 60, 0.866. Square root of 3 over 2. Okay, what do you get when you combine those first two together? Yeah.
Square root of 2 divided by 4.
Square root of 2 divided by 4. Now this is going to become a minus because of the negative right there. What do you get when you combine those together? Yeah.
Square root of 6 over 4.
All right. And now the final answer, we just put it all together. Square root of 2 minus square root of 6 over 4. And again, you can type that in, see what you get. And then type in sine 195 and make sure they match, but they will. Okay, any questions on those? So those are the four really that we're going to look at. There is a sum and difference formula for tangent, but we're not going to do it. Okay, we're gonna hold off on it because if you really had to, I think you guys could figure this out because we know from the last section tangent is the same as something divided by something. Does anybody remember what tangent is the same as? It's the same as two other trig functions divided. Yeah?
Sine and cosine.
Sine over cosine. So if you really had to do a problem with tangent, you could break up tangent as sine divided by cosine, and then do the sine of 15, just like I showed you, and then do the cosine of 15, and divide your two answers when you're done. So a tangent problem this way would be more work, because you'd really have to do two problems. But you could figure it out that way. We're going to skip the actual formula for the sum and difference of tangents. Okay, you can see it looks a little bit different. You don't have to write it down, but it does look a little bit different than the sines and cosines. But the way you prove this formula is actually to do it like this. Take the sine formula I gave you and divide by the cosine formula, and you do get the formula that I showed you. All right, so the last thing we're going to look at is we know what happens when we have a plus or a minus inside the parentheses. We've got a formula to fix that so we don't have the minus there anymore. Well, the other thing that we're not going to want to have inside the argument to a trig function is a number. We generally like to just have a letter, like sine x, cosine x. Not 2x, not 3x, not 4x, just an x. So how do we get rid of this 2? Well, you cannot just take the 2 and say, I'm going to put it in front and call it a day. No, that doesn't work. But I'm going to show you a formula that you can use to always get rid of a 2. And you can get rid of a 3 or a 4, but it starts to get very complicated the higher and higher you go. It starts to get very big. The problem gets huge. So let's try and see if we can get rid of a 2. And I think you guys can already do this based on what I taught you. What's another way that you can think of 2x? I want you to think of a calculation that when you do it, it will give you 2x. And it's going to turn into a formula that we've already learned today. Yeah? X plus x. Now this is the sine sum formula. First, second. It's just the first and the second are the same. So that's going to help us to combine the terms. So let's apply the sine sum formula to this, and that'll tell us what sine 2x is. Okay, when we do the sine formula, are the trig functions grouped together, or are they mixed? Yeah, mixed. They're mixed. Sine, cosine, cosine, sine. what symbol goes between them? Plus or minus?
Minus. Oh, plus.
Plus. When you're doing sine, you keep the symbol the same. When you're doing cosine, you switch it. Okay. Now, first, second, first, second. What's my first?
X,
What's my second?
X,
What's my first?
X,
And my second?
X.
What's the difference between this and that? Yep, nothing. That's the same as that. So I basically have, so then how many of these things do I have if they're exactly the same? Yep, I have two of them. I have 2 of the sine times cosines. Sine times cosine, cosine times sine, same thing. So this is how you get rid of a 2 inside the parentheses. You can use the sine sum formula, and that's the result. From now on, we're just going to jump to that result. Sine 2x is equal to 2 sine cosine. That's how you get rid of a 2. And that's the highest number that we're really going to have to get rid of. So I'm not going to go through and prove all of them. I did do we just did example 4, so I proved that. The symbol that you use here doesn't matter. Use an x, a y, a theta. It's just a variable. But that's what we just did. Yeah.
Does that formula also work for the cosine formula?
You could figure out what would work for the cosine formula by thinking of it like this. Let's see what happens. With cosine, are my trig functions grouped or are they mixed? Grouped. Cosine, cosine. Sine, sine. What symbol goes between them when we do cosine? This is a plus right here. So what do I put here? Put a subtraction. Okay. What's my first angle? Second angle? First angle, second angle. Now, are these two things the same? No. So it's not the same like it was in the last time. But what is cosine times cosine? That's cosine squared. And what's sine times sine? Sine squared. So that is the formula for how you get rid of a 2 in a cosine function. Same idea how you prove it, but it's a very different looking formula than for sine. It's cosine squared minus sine squared. And all these formulas that I'm showing you are what we call double angle identities. When you have an angle that's been doubled, and you want to get rid of the double, get rid of the 2. This is how you do it for sine. This is one way to do it for cosine. Cosine squared minus sine squared. I just proved that one to you. Here's another way to do it. And here's a third way to do it. So the thing that's a little tricky about cosine is, which one of these do you use? Well, depends on your problem. You can use any of them. It's hard to say which one to use because I don't know what problem you're using it on. If the problem said to rewrite the following in terms of just sine, well then I would say use the second one because that just has sine in it. If the problem said rewrite in terms of just cosine, then I would say use the last one. But we'd have to read the directions and see what it says. And like I did with sum and difference, there is one for tangents. We are not doing the tangent one, we're going to skip that. Because if you really had to, you could think of tangent as sine over cosine and really do two different problems and divide to get the final answer. That's what the tangent one looks like. But we're not going to do it. Any questions on that? Yeah.
Are tangents going to go in tests or not going?
No. No. Sines and cosines, yes. All right, let's try any of them. So the directions here say to write 2 cosine x plus sine 2x using only sines and cosines. What that means is no 2's in front of x's. You can have a 2 out front like that, that's fine. But they want sines and cosines in the final answer. Well, that part is fine. 2 cosine x already fits what they want. So we don't have to change anything there. Plus, I mean, what would you change there? It's cosine with just a 1x. It's not a sum of 2 things, it's not a difference, and there's not a 2. So what are you going to get rid of? There's nothing to get rid of. But how about this second part? Sine 2x. Does anybody remember how we rewrite that without the 2? We don't want to go back through the proof every time to figure it out. We just want to remember the result here. Yep.
Sine x plus x.
Well, it would be sine x plus x, but then we have to go back through and simplify all of that. And my question is, what do you get when you simplify that? Yeah?
2 sine x plus x.
Yep. 2 sine x, cosine x. Now, technically, we've done what they wanted. It said to write in terms of just sines with x's and cosines with x's. So we've done it. But what we're going to have to do with some of these problems later in the week now is factor it. Factor means pull out whatever they both have in common. Put that in front. And then put parentheses next to it. What does this term and that term both have in common? Yeah?
The 2 and the cosine x.
They both have a 2 and a cosine x. If you factor 2 cosine x out of here, what would be left right there? So when I do distributive property, I would get back what I started with. Yeah.
You just did, never mind.
Anyone think they know what would be right here? Yeah?
Just sine x.
So remember, you're focusing on this. So this times something has to give you that. Like if you distributed this back out, I want to know this times what would give me that. Yeah? Yeah, 1. That would go there, because 2 cosine x times 1 would give me 2 cosine x. And what did you say for the second one? Let's check it. 2 cosine x times sine x is 2 cosine x sine x. Yeah, perfect. So this is the final answer taken one step further, where you factored out what they had in common. Directions didn't say to do that, but I know tomorrow we're going to have to do that. Any question on it? I think that was it. So actually, we got through that a lot quicker than I thought. Does anyone want to see one more like that? Okay, let me just make up one more. let's do cosine 2x minus sine x, same directions. Is there any part of that that is okay and we don't need to change? Yeah? Yeah, the sine x is fine. So let's leave that. How about cosine 2x? How could I rewrite that so it doesn't have a 2? Yeah?
Cosine x plus x.
And then what do you get when you simplify that whole thing? That's what we want to do in this problem. We want to put that simplified. Caleb?
Cosine 2x minus sine 2x.
Which one of those did you just use?
Cosine 2x minus sine 2x.
I don't see that as a choice here.
Isn't that the first one? The one that.
Oh, cosine squared.
Oh, yeah.
Yeah, cosine 2x would be something like this minus sine 2x. Yeah. So cosine squared minus sine squared. Yeah. So we could do cosine squared minus sine squared. And that satisfies what they wanted. We've written everything in terms of sines and cosines with no numbers in front of the x's. Now, there were other versions of that formula you could have used that would have also been correct.
So you just leave it like that, you don't solve it any further?
There's nothing to solve further because this isn't an equation. Now, if I did something like this, well, that's what we're going to talk about tomorrow. Now we have an equation where we can try to get the x by itself. I'm not sure that would be doable in this problem, but we're going to do ones that are doable. Any questions? Yeah.
Can you factor that out at all?
You could. You can't factor something out of all of them, but these two have a sign in common. So you could do something like this. Let's see. We could factor out one sign from here and one sign from here. So if we did that, we would have something like, in fact, I can even factor the negative out with it. They both have a negative. So I could take the negative and I could take the sign and put that in front. And what would that leave me with? If I pull one copy of sign out from here, I'm still left with one copy. And if I pull one copy out from here, all I'm left with is a 1. The way you can check it is distribute it back out. Negative sign times positive sign is negative sine squared. And negative sign times positive 1 is negative sign. So that's about all the factoring you could do on this problem. It doesn't factor quite as nicely as the last one. But this answer is also correct. Any questions on that? Was there anything else that people wanted me to maybe go back through or put a formula back up for anybody to copy anything down? Do people feel like we went too fast? We got through that a little quicker than I thought. Okay. I need to adjust that. That's not. It's going to be about the same number of questions. I'm just changing the actual questions. So 1, 3, 5, 6. Let's do 9 and 11. 17 and 18. That's fine. So those are the questions for tonight. 1, 3, 5, 6, 9, 11, 17, and 18. So if you do not write it down, make sure you check the video from YouTube today because this is not the same as the video I have online.